Okay, great. Thank you for coming here and sacrificing your lunch to see me in this lovely suit. I'm here to talk about the last 4 years, which have been very, very eventful here at TU Delft. And some of you were involved in it, so thank you for that. And my thesis topic, as you can read over there, it's an Algebraic Multiscale Framework for Fractured Reservoir Simulation. And hopefully by the end of 20 minutes from now, we will see what that is all about. And as some of you might know, I recently moved to a new country just before defending. And I meet a lot of new people these days. And the first question they ask me, especially if they're not involved in petroleum, is why would you involve yourself in this? Why petroleum? It's such a environmentally unfriendly branch to work in. And why don't you instead focus on something like wind energy or solar energy or any number of renewables that we see that are now emerging, which is actually very good news. And they also say that their electric company, when they send their bill, they say, hey, we are giving you 100% green energy. And I was surprised by this myself, because if you look at the facts, you see that renewables are there in the pie chart, but they're not the majority. We are still using a lot of petroleum. We're still using a lot of coal, unfortunately, which is very, very polluting, and natural gas. And then the renewables are starting to emerge, but there will be some time until we get there. So we will need fossil fuels. And it's an exciting topic to work on. So that's why I'm here. That's why I'm looking into this. And it's still going to be there for a while. Because people also say there is no more petroleum in the world. Given a couple of years, we're not going to be able to use it. So what do? We need green energy. And I agree, we do need green energy. But it is not true. There is a lot of petroleum out there. When you take petroleum out of the ground, you use wells, of course. You usually inject water or gas through an injection well. And then you hope to sweep the whole rock containing oil onto a producer well. And this would be the ideal case. Everything gets swept towards the producer. But ideal is not reality. Because what usually happens, you get what is called fingering. You get some preferential paths, and the water only sweeps some part of the reservoir. And then some oil is left in place. And this can be for a number of reasons. First of all, because petroleum reservoirs are layered, and these layers have formed over millions of years, and they have different conductivity. Some of them flow better, some of them don't. So that's why you get this fingering. And the other reason would be that there are fractures in the rock. It's not just a sponge, you have fractures. And these fractures can help flow and then make a direct flow. So you get these fingers because of them. So these two combined can make you have an unfavorable sweep for your reservoir. And there's a lot of people in the audience that are working on enhanced oil recovery. In other words, how to sweep more. And even if you zoom in to the grains of the rock, you get a picture like this. There are oil wet rocks, and you see that the oil is sticking to the grains. So if you push the water will just bypass this layer of oil on the rock, which will stay behind. And then if you think about water wet rocks, which is the opposite scenario, that's not much better. Because now the oil is in the middle of the pores, and then the water just goes around it. So we still don't have full recovery. In fact, what we can recover from a petroleum reservoir with traditional methods is about 20 to 40%. There's a lot of oil still there to be used, even if we don't find new sources of oil or new reservoirs. The old reservoirs still have a lot of oil in them. So there's a challenge how to get that out. And people in the audience have been working on EOR, as I said. So how to sweep that more. You can use a lot of chemicals, make foam. For myself, I am not really looking into that. I'm looking into how do we predict how much we can get beforehand. So maybe a couple of decades before, we know how much we can get, and we can use that information to optimize. In other words, I'm doing reservoir simulation, which takes a body of rock with oil in it, can be fractured as well, and it gives you a response. So after this amount of time, you get this configuration. You have the water here, the oil here, and the gas, and then you know, and then you can use that information for your decision making. It doesn't happen in one go, but what you use for it is a bunch of mass balance equations, a lot of math, and use a computer to solve those equations for you to get your result. And there's a couple of steps you have to take here. First thing is you have to consider space, and you have to discretize your space, because nature is continuous, but computers can only see so much. When you take a photo of a landscape and you zoom in, you see pixels, right? You have the discrete information there. It's the same here in reservoir simulation. You get pixels or cells, And that's the resolution that you're going to get your result at. The finer the resolution, the better the picture, and the more expensive it is to solve, because you're going to have an equation for each cell. So it can be billions of cells. The other axis, if you want, it's time. You can't just go from time 0 to time 20 years from now. You have to discretize the time axis, and then you get steps, time steps. So you have to do this repeatedly until you reach your goal. So the two ingredients in space and time are the cell size, so x, y, z, how big these cells are, and how long your time steps are. The longer the time steps, the quicker you're going to get to the end, but also you lose accuracy. So what are the, if you put units on these, you have a kilometer-long reservoir, and then your cells can be sometimes centimeters, because rocks are very heterogeneous. You get a lot of changes in the conductivity. But if you're talking about fractures, fractures can be millimeter in aperture. So that's even more drastic. You need a lot of grid cells to capture these fine yet important details in your rock. And in times, you're talking about days, sometimes months, and the whole life cycle of the reservoir spans over decades. So there's a lot of time steps to consider, and a lot of resolutions, high resolution features to resolve for each time step. So a lot of work for a computer. And on top of that, there is uncertainty, because as you know, reservoirs are deep down in the earth, there's kilometers. Sometimes they're offshore, so you also have a column of water on top of the rock that you have to measure through if you want to get an idea of what's going on down there. So this leads to a lot of uncertainty, a lot of measurement error, you're not sure. So you don't do one simulation, you do an ensemble. You take a bunch of scenarios, maybe 100, and then you do that process with the time decomposition and space decomposition for all of them. So that's even more work to do, a lot of work actually. So one simulation has to be quite fast for us to get a reasonable answer within a time frame that we can use the information, right? Hence my work. I've been working on an efficient way of doing the simulations. So once you do these scenarios, you're going to get not one result, but a band of results, and you can put some uncertainty bands saying, worst case, best case scenario, and my truth or my reality will be somewhere in between, we hope. A lot of complexities here, right? So there's trade-offs. How do we get this within a reasonable time? Now I'm going to take again the example of photography. When you take a picture of a reality in the old days, when it was just emerging, digital photography was at its beginnings, you had a trade-off. You had only this amount of space on your memory card, and you wanted to make very clear and nice pictures. But you can only store so many clear pictures on that memory card. So if you want high resolution, you're going to be limited to maybe 10 to 100. Or you could choose to have a very coarse or pixelated picture, and then you can store a lot of these, but then maybe it's a bit pointless because you're not going to see what's actually going on. You don't want memories looking like that. So there is a trade-off, and people invented JPEG, which is a very nice format for pictures, because it gives a trade-off between that. You lose some accuracy, there's an approximation in your image, but if you don't see it, it's good enough, and then you can store a lot of them. It's the same in reservoir simulation, because again, you have high resolution, low resolution, and then there's in between, which I've been working on, is multiscale methods. How to get a good resolution, an approximate result, but not solving the full resolution problem, so cheating and going on the coarse scale, and paying for that only, and then you get a good trade-off, which you can actually choose how much accuracy and how much time you're going to invest in it. Sounds great, right? So multiscale methods, what are they? You take a body of rock, you have equations to solve, which is usually a linear system, AP is equal to Q, and you have two operators, restriction and propagation, and these operators allow you to go to a coarser scale, solve the problem there, and then interpolate back with prolongation to recover an answer in the fine scale, which is approximate. So to take this a bit more in layman's terms, say it is Christmas, and you are waiting for Santa to give you a result for your reservoir simulation. But Santa can only give you a coarse scale result. He can only do so much by himself. Now, luckily, Santa has a bunch of helpers, which we call basis functions. And each helper is responsible for one of the coarse blocks, and it knows how to take this information back to the fine scale. In other ways, it's an interpolator. It has a weight multiplied by the value to give you the details. And that's how you do it. And this is how one basis function would look like. You can see it's not a spherical shape. It has a lot of, it basically adapts to heterogeneity in the rock. So based on the properties you have there, you get this response, and then you interpolate your response back to the fine scale using the geological information. That's the whole idea. Now this is in the unfractured case. What happens if we have fractures in there? Obviously, Santa will have more work to do because fractures are also important. They also need to be accounted for. So what he does, just hires more elves. He has a lot of new basis functions which are going to take care of the fractures. So it's a set of rock basis functions, a set of fracture basis functions together. They will give you the result. That's what actually I've been working on for the first part of my PhD, how to model fractures with multiscale methods. And it seems to work. And how fast is it, you might ask? So I did a proof of concept implementation of multiscale for fracture media, and I compared it over several bigger and bigger cases and more complex cases against what is an industry standard, SAMG, which is used by companies like Boeing and such to solve their problems. And you can see that my method, which is in FAMS in red, can be fairly competitive. So given a higher and higher problem, it's pretty close in terms of CPU time, which is measured there in the bars, with that. So we are pretty close to that, and that was a good result for myself to see that it's possible to match the industry standard with what we have. And given more improvement of my code or a better implementation, you can get even more. There's actually a paper from Chevron. They get a 10 times faster result using multiscale methods. That's very promising. And that's what you want. Now here's another brain teaser for you. We have multiscale fractures, but are fractures always highly conductive? In other words, are fractures always the ones that take all the flow and push it forward? What happens in the opposite case when you have fractures that are blocking your flow? So, for example, they are cemented and then the flow has to go around. Instead of helping you get water through, then they will have to be like an obstacle for your flow. Now, this has not really been studied so much in the literature because people focused on the first case, and the fracture model I was using was not really capable of dealing with this case. So I had to extend it a little bit to be able to do that. And then a lot of time in my presentations during conferences, I spent saying, why is this important? And I showed plots like this. So say you have a rock with a lot of fractures in it, and see on the right side, you have a blue streak of diagonal fractures here, and those are blocking. So what happens if those fractures are blocking? How important are they for the behavior of the reservoir? You can see also on the left, the rock has a lot of heterogeneities. There's higher conductivities in the yellow areas, and blue is where it will not flow so fast. And the flow happens from left to right. See, the pressure is 1 on the left, so high, and 0 on the right, so the water and the oil will go from high to low pressure, so it will try to traverse this rock through the fractures. And this is what happens. You see the water going in, starts to go through the high-prone fractures, and then it hits a barrier there. And it cannot pass this barrier, so it has to go around. And there you go. Fractures are important. Hypermobile fractures are even more important. Whereas if you didn't account for this, what would happen? You would just bypass this barrier, and you would get water already very early in your production. So if you base on your decision making on the right result, you would be misled. Whereas the left result would give you a better estimation, all things considered. So I extended this fracture model to capture the improbable fractures, and it seemed to work. So I was happy with that. So this leads to conclusions. What have we seen? We saw that oil and gas is still an important factor in global energy. We cannot just dump it overnight and switch to green yet. Reservoir simulators can be important to give us more insight on how to produce more oil and efficiently produce new reservoirs that might be discovered in the future. And robust simulations, so those that take into account uncertainty and all the geological detail, they can be quite expensive. We need a couple of scenarios, high resolution, small time steps. Everything needs a big computer, sometimes not even feasible on the biggest computer we have. So we need efficient simulations, but still we do not want to give away detail. We still want to keep a good resolution there. And one answer to this is multiscale methods. I show you that they can be efficient, but they don't provide fully accurate results. They have an approximation factor, which we can tune. My development or my contribution to this work was to do this in fractures. What I call FAMS is a multiscale method for fracture media, which has been tested and compared to the industry standard and shows good, promising results. And finally, there is now a model for for impermeable fractures, not only hypermeable fractures, but also the opposite. And everything in between can also be captured. So fractures are important, whether they are blocking or whether they are fluid highways. And they both should be taken into account, and we managed to do this. So with that, I would like to thank you, and if you have any questions about this, please ask now, because if the committee comes, I don't think you're going to have another opportunity. We still have about 15 minutes, 5 minutes or so. Yeah.
Are you thinking of contributing to the sustainable energy industry later on?
It's something that's in the back of my mind. I don't know if my skills that I have now are necessarily good for that, or wind energy or solar energy, maybe for geothermal, they can be used. Yeah, something that I'm considering right now. I still have a lot to learn from petroleum. Petroleum is not an easy to handle fluid. It's a mixture of components. Some of them are light, so they might evaporate if the pressure drops. Some of them are heavy, so they don't move as easily. It's not, maybe water is a bit simpler in that respect. So I think I have a lot of things to catch up on the physics, chemistry, and so, which is not really my background. So I will stick with petroleum for a while at least. Let's see what the future brings, I don't know. But it's a good thought. Thank you. Anybody else? No? Hey,
Hi, Matei. First questions generally, how do you like it in Britain, and where do we? What is your personal thought on what you're working on now?
Well, it's a whole different world. Though it's also reservoir simulation. I'm doing it in a company called Schlumberger in Britain, and. Well, when I was here in TU Delft in the office, I came and I picked up where I've left off the next day. And I did that thing for the whole day, maybe next day as well. And now there's a bunch of branches. There's a lot of multitasking I have to get used to. There's meetings, there's people that ask you about bugs in your code. There's so much that you have to kind of shuffle, and I'm not really used to that. Something to learn, definitely. The weather is not much different than here. So not an upgrade there. The food is okay, but not great. The people are friendly, I like that. I was usually in Delft with friendly people here as well, so I'm used to that, but it's not only Delft. Britain is also welcoming. I'm happy with that. It's not too far away from here, which is also good. So I get to see some of you once in a while, once a month. Overall, it's been good.
And then the second question is about the model that you talked about community. So you imagine that the Santa and the helpers that you make,
Yes.
that it means that the Santa just also hire more and more mathematicians, or actually hire different kind of help, or what?
You know, Santa cannot hire too much help because it gets expensive for him, and that's the same here. If you want too many basis functions, you're going to spend so much time computing them that the simulation gets delayed, and then you're going to end up with the same time frame as if you would do the full resolution simulation. There's a trade-off there. So you don't want too few of them because then you're going to spend a lot of effort trying to use those helpers. They're not going to be very effective. Now, if you have too many of them, they're going to be expensive. And you have to be smart in where you place them. So where you coarsen your grid. If you are given a grid, you should maybe be smart about making a coarser block in some areas which are high permeable, for example, and more detail around the fractures. So that's one thing to consider. And also specialized help is good. So if you have basis functions in the fractures, and fractures are indeed playing a big role in your simulation, and that's a good place to place them. If fractures are somewhere on the side of the reservoir and nothing's going on, maybe it's not a good idea to put that more emphasis on them. You have to be smart, and it depends on the case-by-case basis. And I think people are looking into doing this automatically, but it's still an open question. So you could do another PhD, or maybe a couple of PhDs on this topic.
So educate the else and something.
Yeah, be smart where you put your effort. If you have a simple problem, you don't need much help, but if you have a difficult problem and you're not aware of it, you might be stuck. Okay, who is here a petroleum engineer? Can you raise your hand? Well, quite a few. And how many of you are doing experiments? Well, about half. So if I would have asked this question when I started my PhD, I think most petroleum engineers would have raised their arm when they were doing experiments, because many people are doing experiments, were doing experiments that time. We were a bit of a minority in modeling, and now it's slowly shifting. Hopefully we don't take over fully, because we need both halves to work together. But it's a good sign. Well, the committee will come in about 10 minutes, so we can just relax until then.
Gaat u zitten.
Ik open de zitting van de commissie ter beoordeling van het proefschrift en de stellingen van Matei Tene, Master of Science in Applied Mathematics, Delft University of Technology. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern and the paranyms to take their seats. A warm welcome to all of you at this public defense by the candidate of the dissertation entitled Algebraic Multiscale Framework for Fractured Reservoir Simulation. The Board for Doctorates of Delft University of Technology has installed a committee to evaluate the thesis and proposition. The committee will have a debate here in public with the candidate, and it's an honor to present to you the members of the committee, to whom I extend a hearty welcome. Over on the other side, my far right, Professor Geiger, Harriet Watt University, Edinburgh, Scotland. Next to him, Professor Cileppi, Stanford University, United States of America. Next to him, Professor Verk, Delft University of Technology, Faculty of Mathematics, and then next to him, Professor Sluis, Delft University of Technology, Faculty of Civil Engineering, Geosciences. Over on this side, to my far left, Dr. Kobaishi, Khalifa University in Abu Dhabi, and to my left, the co-promoter, Dr. Haji Beji, Delft University of Technology, Faculty of Civil Engineering and Geosciences. To my right, the promoter, Professor Janssen, also Delft University, Faculty of Civil Engineering and Geosciences. Thank you all for taking part in this academic ceremony. My name is Arthur Meinert. I'm Emeritus Professor of Water Science Engineering at IHE Delft and Delft University of Technology. It's my pleasure to chair this session on behalf of the representatives of Delft University of Technology. I would now like to start the opposition and give the floor to Professor Geiger.
Father Promovendus, I'd like to congratulate you on a very nice thesis, which I enjoyed reading, learned a great deal about American methods for fractured reservoirs. As a practicing reservoir engineer, I'm very interested to understand how you would use the algorithms that you've developed, CAMS, FAMS, and PEDFM, possibly in combination with each other, to solve real-world problems. At the end of your thesis, you say there's some further work to be done, but I believe there's some applications we can already start using the algorithms today. So could you elaborate on this, please?
Hooggeachte opponent, thank you for a question. As far as I understand, you're asking about the practical implications of my work, which I'm happy to elaborate upon. Fractured porous media is important, and people acknowledge it. I've seen it at the conferences I've been, a lot of talks about it. And not so much about impermeable fractures that I've been looking into and found as equally important. And for example, in unconventional reservoirs, where fractures are artificially induced, this work I think has a lot of applications, because they are the main drivers of the flow in such reservoirs, not the matrix rock. And having a multiscale method to treat such fractured porous media is important. So having a good trade-off between computational cost and accuracy, which the user can actually choose, is important. And that was the focus of my work, and in general, the focus of multiscale methods.
Could we elaborate a little bit more on the unconventional reservoir side? So what, particularly in terms of the physics of unconventional reservoirs, and flow physics and other physical processes, have you already covered in your work that lend themselves to modeling fluid flow processes in unconventional other tight reservoirs?
Sure, I would be happy to. So I've focused on flow arising from wells. That means the pressure is dictating the flow. And there's, that is the main driver of the flow in most cases. And there are extra ingredients which can be considered on top of that. One of them is, of course, gravity. When you're dealing with gas, that is one thing which was not taken into account in my work. And the other one, which I started looking into towards the end, was mechanical deformation of these fractures. So by having external forces, body forces onto the rock, you can drive the flow. And all of these factors combined ultimately give you the production response that you are looking for.
Okay. So you mentioned gas reservoirs. What particular physics have you looked in the first chapter of your thesis?
Right.
It's very powerful to actually study that flow process.
Definitely. And the main property of gas is that it is compressible. So that is one thing I focused on for the first year of my PhD, and I developed this compressible flow for multiscale method for compressible flow. So gas, which changes its volume under pressure. And that is, unlike the incompressible flow, that is a nonlinear problem already in the pressure equation, which you have to discretize, linearize, and solve. And then that means that the basis functions that you use in the multiscale framework sometimes have to be updated themselves over time. It's a time-dependent problem. The conductivities change with the density of the gas, for example. And that means that maybe your initially computed basis functions are not accurate anymore, so you have to adaptively update them. I'm not saying update them all, but as need dictates. So in areas where your properties change a lot in the reservoir, you should update them, and the others can be kept the same, so as to not increase computational cost unnecessarily and still keep efficiency.
Do you believe that updating can be done heuristically, or it can be done based on some a priori measures, or does it need to be done heuristically? Because again, as a practicing reservoir engineer, would like to have an algorithm that is stable, runs, converges, and doesn't crash in every second application and change something in my real world application.
I think heuristic is a big part of updating them, because let's say you don't know your response until you get it, so you can only say so much about the next time step from the information in your current time step. So one measure is, of course, transmissibility that you should look into. So if transmissibility has changed a lot due to the front pass in your location, for example, that is an indicator that the basis function should be updated. If you're in a multi-phase scenario and the REL term is a big factor in your equation. If not, then maybe not. Maybe the previous or the initially computed basis functions are enough. And we actually did some experiments in the thesis showing that, as a rule of thumb, let's say, the basis functions initially computed are good enough. If you would update them, you would spend some additional time in doing that, but the decrease in iterations would not maybe justify that.
So what other processes could lead to the requirement of updating the basis functions aside from the compressibility effect in fractured reservoirs, and where the PEDFM approach comes in very handy? You mentioned transmissibilities.
Yeah, another thing that also PDFM or EDFM in general is strong at is changing configurations of fractures. So if for mechanical reasons or any other reason your shape of the fractures, apertures of the fractures would have to change, the effort you would have to spend on that change is not significant with embedded type of models, because the geometry of the grid in the rock would not have to change. You would just have to change the transmissibilities between them based on those geometrical changes. So that is one forte point, and that's why embedded type of fracture models are gaining more popularity as opposed to discrete or conforming fracture models, where any small change would lead you to regenerate your grid, and that would be quite significant.
In the simulation look at transient processes. A lot of the work, when read your thesis correctly, looks at basically solving one single time step, scalability in one time step. Have you looked at all in the size of the time step, depth of time stepping changes the convergence behavior of your algorithms? Because that's, again, very important for practical applications, especially if you have things like fractures closing and fluid properties evolving because of the function of the pressure field itself.
So, okay, the point, I must admit I'm not an expert on time stepping. It was not necessarily a focus of my work. With that said, I did run some multi-phase cases with which fractures evolved, and that required of course time stepping. And I could see that even though I employed some methods that are known, such as thrust regions and other methods that are meant to make the method conditionally stable, there were some limitations into the time step that I could choose. And that is a topic of further work. Is it because the fractures add extra complexities, or is it the heterogeneities in the matrix? So I cannot stand that much. It's my speculative answer, but that is an important aspect to be looked upon, which I didn't focus my work on.
In your FAMS solver method, you propose different coupling strategies, and continuing with the theme of the practical real-world applications. How would you advise as to which coupling scheme to use? The decoupled one, fully coupled rock AMS, fracture AMS?
That's right. I did a couple of options there. Because fractures were indeed important in those cases, and the way you construct your basis functions to account for this coupling was important. And but at the same time, as a rule of thumb, for most cases, I saw that the simplest formulation for the basis functions, so in other words, where fracture matrices are fully decoupled, was a good enough approach, and it would be easier to compute those basis functions. You would spend less time. With that said, there were some cases that I tried where fractures were driving the flow and then putting more emphasis on the fracture basis function. So a one-way coupled or a fully coupled approach had indeed some gain in it. So it's a matter of practice how you choose this, but if you have no other information about the reservoir beforehand, I think a decoupled or a simple approach to basis functions is a good starting point, if not for the whole simulation, at least for the start.
Can I challenge you on the good enough answer? Are we at risk of missing some physics in some aspects? For example, how fluids transfer from the matrix into the fracture and vice versa. Is that a risk if we use a decoupled strategy?
No, that is not a risk, unfortunately, so for multiscale methods. So the basis functions is only one stage of the two-stage process you use to solve your equation. And whatever is missing, because of the localization assumption, for example, of the basis function, can be accounted for by the smoother stage, which is a fine-scale solver, approximate solver, which iterated long enough can by itself solve your problem. And these two stages work together, and in the end, you can capture all the physics with both of them, no matter what you're simplifying in the basis function formulation.
Director, I have no further questions.
Thank you very much, Professor Geiger, for your opposition. May I invite Professor Chalep to continue, please.
Ard promovendus, congratulations. I read your work with interest. I think this is an excellent piece of work, and it will leave a permanent contribution to the field. So congratulations on that. I wanted to start discussions following up on Professor Geiger's line of questioning. You mentioned gravity as one area. What is your perspective on the importance of capillarity, and what would it take to put it in your framework?
Thank you for that question. So you're asking about extended physics in my framework. How would I include those? First of all, they are very important in some cases, especially in unconventionals. And nevertheless, for my work, I decided to stick to the simpler formulation, simply because my focus was on the method of solving the equations rather than the equations themselves. Now, nonetheless, that is an important factor. an important objective if you want to have a field scale reservoir simulated.
But if you want to just step back and so just highlight what may be the primary challenge that capillarity would offer, say, as opposed to gravity. What is distinctly different that you need to do?
Definitely, sure, thank you for that. So what capillarity does is it introduces a very strong coupling between your flow and transport equations. And in my approach, and many multiscale works in the literature, we use a sequentially coupled approach between these two equations simply because without capillarity, these are known to be weakly coupled, and the sequential approach can gain some efficiency over the fully implicit approach where everything is solved all together. So introducing capillarity would invalidate this assumption in a way, and coupling will be stronger, which means that in your sequential approach you have to iterate the outer loop or the sequential loop a lot in order to account for these changes. But there is a recent work that I'm aware of from Song Lee, where he has a hybrid upwinding method for this, which maintains the sequentially coupled approach and adds extra terms in the fractional flow formulation of the transport, such that the source terms arising from both gravity and capillarity are expressly taken into account, and then the coupling is still resolved within reasonable amount of iterations. So that is one way I would go.
Okay, that sounds good. You mentioned the challenge associated with geomechanics. So again here, what would you do, and what is missing from your current numerical framework to accommodate mechanics?
Thank you for that. So I've been looking into geomechanics briefly at the end of my thesis, and how would we treat that with multiscale methods, coupled flow, and geomechanics. So mechanics is another equation on top, elliptic equation, which is a good news for our multiscale methods, because they are mostly geared at such problems. Also the pressure or the flow equation is elliptic. So what I would have liked to do in my work, and I think is still a very viable future work alternative, is to formulate a multiscale mechanics formulation, which has already started to appear in the literature. You can see Nicola Castelletto's work on that. So you have basis functions for your displacement equations. And then you have, of course, pressure basis functions. And if you add that into for fractured media, then you would have to have, for both equations, basis functions that account for the fracture, deformation, or flow. And still in a sequentially coupled approach, you could use, and I think it would be successful without having done it myself.
No, I think that sounds convincing. I wanted to ask you about your perspective on whether your framework is a nonlinear simulation framework, or is it a linear solver framework, or is it somewhere in between?
This is indeed a point of debate, I think, when it comes to multiscale methods. In terms of linearity or nonlinearity, I started off looking into nonlinear equations with compressible flows. And then later on, for the rest of the thesis, I switched back to incompressible simply because the fractures were the focal point. So I have a bit of experience with nonlinearities, not necessarily the focus, at least for most of the work. And if you could repeat the second part of the question.
Do you think of it more of a nonlinear solver framework, or a way to replace existing linear solvers with more scalable approaches? What is it?
That's right. So you can use multiscale in two ways.
What do you prefer? How would you prefer to see it?
Yeah, so my preference is to use multiscale as an approximate solver. And I think that's where the gain is to be had when it comes to multiscale solvers. And that's simply because there's so much competition in the linear solver part. You have multigrid, which is already established and delivers good results. In my work, I show that we can somehow match the performance there. But I think there's even more gains if you use multiscale as an approximate solver. In other words, you stop at the linear tolerance level and then reconstruct your flux, and then you can obtain approximate results with multiscale at a fraction of the cost of having to do the full fully accurate and fully implicit way of doing solving the equations.
Okay, so based on your long experience through the PhD and what you've seen from the literature and now in an industrial setting, how far is multiscale from practice? When are we going to see it in practice, and what would you do to help that?
Thank you for that question, the opponent. I am now employed by a company in the UK which is actually actively looking into making multiscale a commercial part of their commercial release for their simulator.
That's a good sign.
And that is a good sign. I'm happy to be involved in this effort, having just stepped out of the university. So there will be signs of that coming very soon, I think, and I'm happy to report that.
So if, I know you don't have 6 more months, but if you had 6 more months, what is the burning question that you would want to deal with?
If I had 6 more months, 6 months is a long time, and it is not.
Not so long.
But I would definitely continue my work on mechanics and coupling fluid mechanics, which I've only done in the fine scale. So I only scratched the surface. Multiscale was not was one of my initial objectives in the thesis, which I did not put a full tick against, and I would have liked to see that, and I'm happy that people are picking this work up. We have some master students in this room that have actually looked into that, so I'm happy with that, and there's also papers coming out on the topic.
I want to go back to one of the questions from Professor Geiger, this time-stepping question.
Right.
If you were to distill the essence of the nonlinearity in our problems, where would you focus your effort to improve the time-stepping piece of it?
Mm-hmm. That is I appreciate the weight of that question. Let's see. There's a lot of things to consider when you think about time-stepping, things that are not usually always apparent. I think in the incompressible case, for example, the main source of linearity is the fractional flow and the fractional flow function, basically, the shape of that and the inflection points that you have. Now, when you add capillarity and gravity to that, then the shape of it will change drastically from an S-shaped function to something else. You will have more inflection points to be taken care of. But I think still that is the main source of nonlinearity, our REL curve and our fractional flow formulation.
Media Director, I have no further questions.
Thank you very much, Professor Chilabi. May I invite Professor Fab to continue with your position, please?
Dank u wel, meneer Director, waarde promovendus. I've also read your thesis with great interest. Congratulations. I think also some nice publications coming from this work, so this is nice. As you can expect from me, I will ask you about solvers. Maybe you can put on the beamer page 58, where we see some convergence plots.
Okay, I would be happy to. There we are.
So if I look to these figures, the first question which came to my mind is you see that we have very high accuracy going from 10 to the power 6, the residual, and then going down to 10 minus 6. Is that needed? Do you need it in engineering applications, or are you satisfied with lower accuracy?
Oh, hello, and thank you for the question. So regarding to the accuracy that you need, that is a case-dependent problem. We're looking here, in this case, at the residual norm, which is a measure of the mass balance you would have in your equation. So if you have a residual norm of around 10 to the minus 6, you expect that the mass is reasonably conserved. Now, it's of course a matter of scale. For example, if your reservoir or your pore volume is very small, then at the range of 10 to the minus 6, then losing 10 to the minus 6 of mass is significant. So it is case dependent, but for the size of the domains that I consider, 10 to the minus 6 is really a small number. And I think you can actually aim for more lenient tolerances, so 10 to the minus 1 or 10 to the minus 2 would still be sufficient.
Related to that is it is good to have some idea of order of magnitude of the condition number of your matrices. Do you have an estimate, or what is the range?
Yeah, and I'm happy to comment on that, especially in cases with fractures. Basically, the condition number, let's even step back from fractures. Condition numbers in this case relates to how severe is the contrasting conductivities between different locations in your reservoir. And now coming back to fractures, these are usually the main sources of contrast. You can have orders of magnitude more conductive, or as I consider as well, less conductive fractures than you have conductivities in the matrix. And I saw that the condition number is proportional to this contrast. So in some of my cases where I consider 8 orders of magnitude difference, you can expect that the condition number is, that problem is very ill conditioned.
And if you combine that with machine accuracy, are these reliable numbers?
I understand. Okay, well, yes, you have to consider the condition number when it comes to your tolerance, because sometimes it's not feasible to reach some tolerance below your condition number, let's say. So if the condition number is 10 to the minus 8, you cannot expect 10 to the minus 10 in your residual. So definitely, that's one big ingredient you have to consider. At the same time, computing a condition number is a very expensive problem beforehand, or if you have a matrix, given a matrix. So you could estimate it, and maybe you can use that as a guideline for your tolerances that you should use.
Yeah.
At the same time, with multiscale methods, we aim for very lenient tolerances, so I expect that it's less of a problem in that case, as opposed to a fine scale, fully converged simulation.
I agree with your answer. So then if we look also to these pictures again, so you see several lines with 1 degree of freedom, 3, 6, until 575. And then you see that the convergence or the number of iterations becomes much less. However, what about the cost per iteration? Can you say something about that?
Yes, we can. There's, let me see if I can refer to some of these other plots on the following page, where I report CPU times, and also on the top of each bar you can see iterations, how many iterations. You could divide those and find how much an iteration costs. Now, between the 4 coupling methods, there's not much difference to be said in terms of iterations, because those iterations, as you can see from the colors on the bars, are related to the smoother, which is in this case ILU0 smoother.
Mm-hmm.
So it doesn't have anything to do with the basis functions, or even if there's fractures in the domain or not. It's just a fine scale smoother. So you could say it's a fairly low cost for iterations, but if you have a lot of iterations, then of course it adds up. But the smoother seems to be doing a lot of work in these cases. So the smoother is the main source for the CPU time in this case.
They are comparable, let's say.
Yes.
Yeah. So that means that high number of degrees of freedoms is beneficial for convergence and for CPU time.
That's right, yes. So having less coarse scale for multiscale or more basis functions leads to a reduction in this. Although, as I was telling before to the audience, you have to be smart where you put these degrees of freedom. So you can see, for some of the cases, even though I changed, for example, frac AMS, which is right here, if I increase the numbers of degrees of freedom, then it's not effective, because in those cases, fractures are not a big part of the flow. So if that's the case, putting more degrees of freedom there is not going to be beneficial. So it is dependent on what medium does the flow tend to prefer.
Then maybe you can go to page 64. And this is somewhat related, but now you compare Richardson iteration and GMRS iteration.
Yes.
And if I understand correctly, the Richardson iterations are more or less stagnant, and your GMRS seems to converge better. Can you comment on that?
Yes, indeed. So as from this plot, I'm comparing Richardson and GMRS for multiscale and SAMG. And you can see that Richardson for both methods tends to stagnate around 10 to the minus 4. And Richardson is just an unpreconditioned iterative solver. And with GMRS, which is basically an accelerated method to converge, you can see that both methods can go to a much lower tolerance. And this happens for a test case where the conductivity ratio between fractures and matrix is quite significant. I think it's 10 to the 6th reported here. So 6 orders of magnitude. In other words, the condition number of that matrix is very unfavorable, and this is probably the main source of this stagnation, as we discussed. And with an accelerated method or with a precondition method, you have a better condition number in the resulting system, which allows you to go to a lower tolerance. This is what I see here.
Yeah, so I'm not sure, but let's say for the research from iteration, in general you compute the residual, so B minus A times your approximate solution. With GMRS, in general you have some indicator, some number which you can estimate the residual. Have you used that, or have you used the true residual for GMRS?
Okay, for the development, I've used the true residual and without any restarting in GMRS in this case. And with that said, I'm not an expert on GMRS. As far as I understand, you construct an orthogonal space for the solution, or the residual space. And then after some iterations, you get all the degrees of freedom in that space, and you are finally able to converge. Yes, that is my understanding of GMRS.
So sometimes we have to should look further into that. Sometimes you see that the estimate of the residual is diverging from the real residual. So sometimes it looks as going down, whereas if you look to the true residual, it looks the same as the research. So
I see.
That's I would be somewhat afraid of this. Yeah, but we can look into that. Okay, then maybe a final question. On page 25. So it's all about solvers, sorry for that.
25.
Yeah. So on the top, on the top page, I think you are solving a nonlinear problem,
Yes.
and then you can have different strategies, or go to a very high accuracy, which is the left plot, if I understand correctly, or you do only one order of magnitude, and then you get the right plot.
Exactly.
And again, I see a number of iterations, and yeah, that's not completely sure for me what is a good strategies, because on one hand, the number of iterations is less if you look to the right-hand side, but sometimes in every nonlinear iteration, you have to build your Jacobian matrix, which can be very expensive, whereas doing one or two steps extra in your linear solver is not that expensive. So, can you help me?
Yeah, so let me see if just explaining what I thought about when I made these plots answers the question. Otherwise, please follow up. So I tried to plot the residual norm, which is in blue, which is basically what is measured during a linear solve of one of your linearized problems, which you have to, of course, obtain during the next RF iteration. And the other one is, let's call it an error norm, or the mass balance, basically, which is what you would want to have minimal. And my conclusion is that there's a lot of time wasted in these linear stages of the solve, because getting a very low residual does not, as you can see, translate into reducing the overall error in this case. And indeed, I conclude that one order of magnitude reduction in this residual is enough, and you can save those linear iterations. Now, I agree with your point that this is very much a rule of thumb approach. You cannot just put 10 to the minus 1 on this and hope that you can cover any case. And in some cases, you taking an extra couple of linear iterations might reduce this error norm, and it could be beneficial to spend more time on it. And what is a good way to do that? I think the best way is to compute this error norm all the time and have that as your reference, but that is quite an expensive process. And it might actually offset the cost that you incur just by doing this rule of thumb or doing these linear iterations.
I agree, so there are some strategies with that. So, for instance, at the end you see you get superlinear convergence if you do the high accuracy. And so that can be a good strategy. In general, use 10 minus 1 as a stopping criteria, and later on use a somewhat higher stopping criteria, or accuracy. My final question. My final question is about parallelization. So your smoother is mostly done with ILU 0 or ILU, which is not so good in parallel computing. Can you comment on that?
Yeah, thank you for this. It is true that ILU is mostly suitable for sequential, and then you could turn into looking into other type of solvers. Usually the block type of solvers are very good for parallel, because then you know that each block gets assigned one thread or one process. And there's also a block ILU type of solver, so it is quite a big part of what I'm working on now in the simulator in the company, because everything has to be in parallel, of course, to obtain the most performance out of your solvers. And yes, so block Jacobi would be the easiest way, or block ILU I think would be better, because in my experience ILU itself is a good choice for a smoother edge. Kobe is simply not enough for some of these problems, simply because the off-diagonal terms still play a role. It's not only the diagonal contribution that matters.
Thank you very much. I'm satisfied with these answers.
Thank you very much, Professor Vaak. May I invite Professor Sluis to continue the opposition?
Dank u wel, meneer de rector. Hartelijk promovendus. I'd like to discuss with you the fracture network discretization that you apply in your thesis. A little bit on the quality of it and the particular choice that you make there. It's a regular procedure that people use these discrete fracture networks, and then the crack runs basically along the edge of the element, along the matrix cell edge. Meshing becomes very complex in that way, and I think when the crack pattern is very dense, meshing is no option anymore, right? So it becomes too complicated almost. So it's better that what you did as well, to superimpose the cracks on a background mesh, you can say, a structured background mesh, which makes it easy as well. That gives you much more flexibility, but there are different concepts there that you could follow. And what you did was basically you use the embedded discrete fracture models, the EDFM model, but there are other concepts around as well. Also in your community, people nowadays, they use the extended finite volume method, or the XFEM method, and that's another concept with along the same ideas. You use EDFM, and you upgraded it because you did the projection-based, EDFM method, that you could not only model the highly conductive crack, but also the barriers, and that's a big advantage of what you did. But nevertheless, you're quite brief in the thesis on the particular choice of this discretization technique. So I'd like to ask a question a little bit on this. Why did you do this? Why did you choose the particular EDFM concept? Also in terms of the ability of the concept to realistically describe the crack, but also in terms of computational issues, robustness, is the procedure costly or not? And also in terms of programming, sometimes what people see, for instance, in these XFEM, that they result in system matrices which are poorly conditioned. So how is that in the case of your network? So a number of criteria that you probably have used for the choice, the particular choice, and I'd like to know a little bit more about this.
Okay, hello, and thank you for the kind words and the elaborate question. Let me take it step by step. Indeed, in my work, I was compelled to choose the EDFM type of approach, and that decision stems mostly because the end goal of this thesis was to look into fracture mechanics, and we expected to have fractures that would deform or the apertures would change, and then having to reconstruct a grid for a conforming DFM approach would have taken most of my PhD away from something that I would like to focus, which is multiscale methods, not grid regeneration. And you also mentioned the extended finite elements, and I think those are very popular in the mechanics community for fracture mechanics, and they follow a philosophy similar to EDFM in the sense that the fractures are not conforming to your elements in this case, and you use some shape functions or enriched space of shape functions to capture them. And I have also thought about it when I did my mechanics part of the work, and one of the key challenges that I found with XFEM was when you have an intersection of many fractures between one element, those shape functions would get very complex, and the geometry of those intersections would be very important, and they would all be focused in one element. And I think that is one nevralgic point of these methods which has to be looked into. Either you could circumvent it by defining a grid in that area, and that would be an easy way out, you add more elements, or you would have to compute some very complexly shaped basis functions. And those systems for the basis functions, they might also be very ill conditioned because of this geometry. But I have no experience having done that. I would have liked to. That would have been, as Handy said, 6 months from now, I would have liked to see that.
Yeah, but also your case, because if you extend it to 3D, and I would say truly in 3D, because if you look in your examples, they are in 3D computations, the cracks are all vertical, I would call it 2.5D almost.
Yes.
And if you really have inclined cracks, do you not run into the same type of trouble with intersecting cracks?
I think the intersecting fractures is even for EDFM, especially the projection-based EDFM that I propose in my work here. You still have some geometric constraints to think about. Let me see if I can quickly find the picture that describes that. But computing these projections in the presence of very complex intersections of fractures is also not something easily imagined in such cases. And that is because these fractures will start competing for the interface area. And deciding which gets what is a tricky problem. And also, you have to make sure that these fractures or projections are continuous. There you go, finally. See, so each element would be projected onto the interfacial area. And having too many elements to be projected, then you have to decide which one gets that area. And at the same time, as you see here, and also in some of the publications from Tulsa University, where they looked at EDFM, and they emphasized the fact that these projections have to be continuous. If there's any hole within this red line here, then having an impermeable fracture would not be effective because that discontinuity would allow the flow to happen, and then you lose a lot of information, or you don't get a good result from your simulator.
Yeah.
So it's fracture intersections are a challenge for both methods, I think.
I think so too. A little bit on the comparison of your method with, for instance, the discrete crack modeling. You do that, for instance, on page 92. You just showed the figure, yeah. So figure 4.15, right? Which is nice. There you make a comparison between the more traditional DFM, one would say, and your projection-based EDFM procedure. And I miss a little bit, because this is a nice comparison, but I miss a little bit the quantitative comparison, because you only said, well, the pictures look more or less the same, left and right, and the conclusion is they are in good agreement. But I think you probably made a more thorough comparison here.
Okay, so here is my attempt to do that here. Indeed, we compared DFM, although as you said, this is still vertically inclined fractures, but nevertheless, you can use DFM or EDFM and compare them here. And I stopped in my analysis here just to a visual comparison, if you will. But with this visual comparison, I still stand by it in the sense that you can see some of the complexities already in the shapes of these isopressure curves. And you can see the effect of the unstructured grid on those versus the nice contoured shapes that you have for the structured grid with EDFM. So it was a nice annex to my work, not necessarily the focus. So I agree that the more in-depth comparison between these two methods, especially if you consider commercial reservoir simulation, has to be done to see which one is the best candidate.
What would be your speculation?
Okay, my speculation is that actually it's based on what I've heard from the industry, that some cases require so much time in the grading part of the process of the reservoir simulator that it is DFM for some fracture cases is very expensive, and having the alternative of the EDFM, then this grading would not, or the complexity is not offloaded on the grading, but it's offloaded on the transmissibility map, which is a different area. So I think if EDFM is shown to have a competitive advantage, or even be the same as DFM, just not having to do this complex grading is already a very good selling point for it.
Okay, thank you. I'm happy with the answers.
Thank you very much, Professor Sluis. May I invite Dr. Kobayashi to continue the opposition, please?
Thank you, Mr. Director. Worthy promovendas, congratulations on the marvelous work you have accomplished so far. And my comments/questions would be mostly again from perspective. So the moment we'd like to tackle a real field application as heavily fractured or netly fractured reservoir, we'll end up with a corner point geometry grid to begin with, or at some point even unstructured grid. Can you comment on the complexity that that can impose on the PEDFM formulation? And do you see this growing into an MPFA type of approach, and then we'll start worrying or looking into monotonicity issues? Because most of your work has been based on a two-point flux approximation, right?
And thank you for that question. And it relates to TPFA versus MPFA, which is a very good point here. Indeed, my work has focused on two-point flux approximation, which means that the flux is given by the two cells surrounding an interface, rather than taking a stencil which has influences from other cells. But with that in mind, as I think I briefly comment here, when I introduce PEDFM, there's extra connections to be considered simply by its formulation. And in a way, what it was before TPFA in EDFM becomes MPFA with PEDFM. Now, of course, this will not have any effect where you have no fractures, but near the fractures, instead of having flow from the yellow cells in this plot to the fracture only, I also involve the orange cells, which are not touched by the fracture elements, but they are adjacent to elements that are fractured. So in this area, you could argue that there's free actors into the flow. There's the fracture and the two cells, or sometimes even free cells. If let's see, I think this element you could say that it has influences from more than free cells. Now, I agree with you in the sense that even in the unfractured case, MPFA was designed initially to avoid oscillations or artifacts that arise from TPFA in some cases. And I have not looked into that for my matrix calculation. And I could only speculate that it can bring benefits, but it can also cause additional artifacts sometimes. MPFA adds an even more stronger spatial coupling between the unknowns. And if you have very discontinuous permeability or conductivity, having a connection between elements that are far away from each other can introduce additional oscillations. So it's not a solution yet. We have to see what compromise we can reach between the two. Where is MPFA good and where TPFA is better?
The projection by itself on the interfaces, would we have to revisit that, or would it exactly remain the same?
Yeah, I recall your question about unstructured grids, so let me also refer to that. If you would have unstructured grids for your matrix, and you would want to implement PEDFM on those, the complexity will not be much bigger than having just a structured grid. It's a matter of finding the candidate interfaces, or these red lines. So even if these would be triangles, you would not have that much issue. The only requirement that I would impose on that is that they still form a continuous surface. There's no breaks in them. As I said, that's important for impermeable fractures to be taken into account. But even if these would not be structured, I don't see that much complexity.
So another comment or slash question I have is, how straightforward would it be to add more physics to your approach, in the sense that not all flow problems are pressure driven? So let's say in the case you just have gravity or capillarity, or in some cases even diffusion flow, like dictating the flow mechanism, which becomes very important in production of fractured systems. So it's not necessarily the convective flow that we always think about. How easy or difficult is it to add gravity when you do not have some sort of an idealized conceptual model? Think about the multi-continuum models, right? They're idealized models, but you can treat, for example, gravity segregation in a multi-phase flow scenario between matrix and fracture in a very simplistic way. When you have embedded discrete fractures or discrete fracture models for that case, what do you do? I mean, can you comment on that, please?
With pleasure. But first, I'd like to ask for a clarification. Are you referring to the fine scale or the multiscale, or is it not important?
Fine scale.
Okay, fine scale. So if you would have additional physics, such as gravity and capillarity, you would have a different transmissibility in your system, and you would possibly add extra source terms because of these effects. And also, you might change a problem from being linear to nonlinear. So there's a bunch of complexities. Now, having said that, having fractures with these physics present with EDFM, let's say, is not a big challenge in terms of your equations, because that would just mean that you have extra control volumes to account. So you would have extra equations, but they would be the same shape or the same nature as the matrix ones. And you would have extra off-diagonal terms, and you would have probably not such a good sparsity pattern in your matrix anymore. If you would have a structure grid, you would expect a diagonal structure in your matrix, whereas here any fracture element can potentially intersect with any matrix element. And unless you have some careful ordering of your unknowns, which would give you a good sparsity pattern, you should not expect to have such a well-behaved system anymore. Those are the complexities with fractures, even without these physics included. And the extra step that you have to take in the sequential implicit is that you have the coupling to resolve using Newton-Raphson. And depending on the strength of the coupling, then you would have to spend more time doing sequential iterations, or you could opt for an adaptive implicit approach, for example. So only have implicitness where it is actually needed, and then you would probably save a lot of time.
Dr. Kobayashi, are you satisfied?
Yes.
Thank you very much. May I invite the co-promoter, Dr. Algebraic, to continue the opposition.
Thank you very much, Director. Varda Promovendus, dear Matei, congratulations. It's been a pleasure to have you here for the 4 years, and glad to see you here standing up. I have a very quick question and then follow-up quicker questions. You assume, given the fracture map, we know what to do the rest. But coming up with a characterized fracture network map is not a trivial task in our geoscientific practice as well to do. So, to that line, if I have a very, very dense fracture network, you have done marvelous work in treating them and accurately and efficiently resolving them. But are all fractures equally as important as each other? And can we be smarter in a way that we detect which one is more important, keep them, which one is not more important, we do less effort for them? Or what would you think or advise on that?
So, the promoter, thank you for your question. And it relates to how do we discern between important fractures and unimportant fractures. And as you are aware of the hierarchical approach for fracture modeling, once we have decided that, then it is a matter of homogenizing the small, or let's not call them small, but unimportant fractures into the matrix, altering its probability, and then explicitly treating the other set with EDFM or something else. How we decide on that, there's a bunch of methods in the literature. There's simple analytical models, which would give you an answer straight away, or you could do a flow-based upscaling for them, which is more expensive, and then you would have basically to solve some small problems to determine what would be that effective probability. As to where the threshold lies, you could simply look at the length of the fractures, but I don't think that is necessarily enough for all the cases. I think the conductivity plays a good role, and also the vicinity of other fractures. Even if you have small fractures, but they are very well connected, they would still be significant. So just cut into everything based on that is not a good approach, I think.
Okay, very good. The next question I have is, what was the biggest challenge in your PhD? Time management or development of new methods?
Second, the promoter, thank you for that question. I believe it was at least it felt like it was the time management. I think that was the main thing on my mind when I was working during the 4 years, and it has led to some very good results. It has been also taking a lot of my brain capacity. Whereas I would have probably wanted to use that more for the actual implementation. But it was always a trade-off between these two. And I think we achieved a good trade-off in the end.
And the last question I have is, what would be your advice to the next PhD student who would follow up your work?
Are you simply referring to the work or the PhD life?
No, the content of the book. Let's give or decide from book to get that.
For the content of the work, well, there's a bunch of branches you could take this into. There's more physics to be added to this and see how that behaves. And there is more to be done in terms of multiscale methods. Well, there's a good coarsening strategy for multiscale methods. I think that was, as far as my results show, that is a very big factor in how the method performs. Even if you have a structured grid, having a, let's call it unstructured coarse scale grid, or a smart way of choosing how to coarsen, and then the basis functions that result from that, would give you an edge with fewer degrees of freedom. Whereas, yeah, that's one thing. I think there's many more.
Any director? I am satisfied.
Thank you very much. May I invite the promoter, Professor Jansen, to continue the opposition.
Thank you, Director. By the Promovendus, I would like to ask some questions about proposition number 5.
Promovendus, could you have read proposition number 5?
Director, yes, I would like to ask my RNA Raphael to do that.
Accounting for modeling errors is crucial when performing history matching and optimization in a closed-loop reservoir management system.
Professor Jansen.
By the Promovendus, of course, I'm quite happy that you addressed optimization and history matching in your thesis, if only in the propositions. And interestingly, you focused there on a particular aspect, on model error. The first thing that springs to mind if we talk about history matching is usually measurement errors. But apart from those two, could you bring up other errors which would be of relevance?
Focus the promoter. Thank you for the question. And this proposition in particular stems from a bit more my experience rather than my work necessarily, because before this I have done my master's on history matching, and indeed I would have agreed fully with you that I would have thought only of measurement errors the main source of inaccuracies in our models. But having done reservoir simulation for my PhD for the past 4 years, and especially multiscale methods, which given the measurement errors, they want to make an approximate solution based given those uncertainties, so it adds extra possibilities of inaccuracies there. I think this becomes a valid point. So if you would do a multiscale simulator and you would want to perform history matching, assuming that there is no scatization error or modeling error in your simulator, and it is perfect given good data, does not hold anymore. I don't think it holds even for the fine scale, but more so for multiscale when you are...
Okay, so we talk about model error, we talk about measurement error. Is there anything else you could prove? So another type of error. Maybe you could ask one of your paradigms to read proposition number 9.
Raphael, would you be kind to read proposition number 9, please? Thank you.
The main difference between a veteran programmer and a beginner is that the latter still has the impulse to blame the compiler for errors in their code.
We talk about different types of errors here. What are they?
Yes, indeed, there would be also human error in this case. If you just refer to the skills of the programmer involved, and there is a rule of thumb saying that every 10 lines of code has at least one bug. Now, hopefully, when you have a good pipeline for your development, for example, in a company, some of these bugs would be caught in the testing framework that you have, but of course, nothing is perfect. So I agree with you, but I would have a very difficult time quantifying such an error while I acknowledge its existence.
Okay, well, I'm glad that you at least acknowledge the existence of human error. I agree that it's difficult to quantify the magnitude of that error, so let's stick to the model error, which you clearly thought about. How could you incorporate model error in your model, your friction model?
Okay, so I think model error with respect to multiscale method is your tolerance that you set for or the accuracy that you would want to get out of your simulator, given that it's a multiscale simulator. And having expectations of the simulator to deliver a accurate result, given that you have some knowledge of your uncertainty in the geology. For example, if you can say that that uncertainty is 10 to the minus 4, why would you ask for your simulator to deliver a result at 10 to the minus 8? So having spent that much time in improving your result is not going to translate into a better decision, I believe.
Yeah, but just put it all in the tolerance is, I think, cheating a little bit. You did hint on geology as a source of error. But can you become a little bit more specific? Which elements of your multiscale model could be explicitly taken into account model error?
I think
and how would you do that?
I think that would be the basis functions, or your interpolators that you use to reconstruct the fine scale information from the coarse scale information. Because you are indeed solving the problem at the coarse scale, so you can say that it is exactly that scale.
But what particular term would you add to your equations to incorporate that model error?
A source term.
A source term.
Yes.
So it's an additive source term?
Thank you, Madam. I request the promovendus and the paranims to return to their seats in the audience. The committee will now withdraw. For further deliberation in the committee room, this session is adjourned.
Wilt u opstaan?
I reopen the session and request the promovendus and the paranims to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft na kennis te hebben genomen van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met in achtneming van het bepaalde in de wet op het hoger onderwijs en wetenschap onderzoek, besloten u de graad te verlenen van dokter. Ik verzoek de promotor door het College voor Promoties als zodanig aangewezen zich wel van hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij de wet toegekend aan het College voor Promoties verklaar ik namens dat college, hier vertegenwoordigd door de rector Martivicus en de overige leden van de commissie, bij deze u, Matei Tene, bevorderen tot dokter en u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren. Ondertekend door de rector Magnificus en de promotoren en voorzien van het zegel van de Technische Universiteit Delft.
Gaat u zitten.
It is the co-promoter's privilege to be the first to congratulate the young doctor. Dr. Algebraic, the floor is yours.
Thank you. Dear Dr. Tene, dear Matei, congratulations many times for such an achievement with such a remarkable work. I remember it was about 5 years ago when Jan Jansen, your promoter, came to me and said, I would just in the master thesis committee defense of an excellent applied mathematics student. What if you interviewed him for the project you have with Adam? I got a copy of your CV from him and talked a bit more with him about it. And then I said to myself, that would be very nice if I could recruit him. So I contacted you for a meeting in my office discussing about your future plans. In my mind, my plan was to do marketing and make you attracted to accept my offer. But obviously, I didn't want you hear that. So, seeing you today standing up here with that red cylinder in your hands, I think that meeting was a successful meeting. You started first by a couple of months working on a project with Schlumberger intersecting until our grant paperwork with ADNOC could be finalized. During that period, you also spent 2 months at Stanford University with Professor Chalepi's team, where Sean Wang was finishing his PhD thesis. After about 4 months, kickoff start, which resulted in 1 conference and a journal paper, you officially started your PhD as of 1st March 2014. It was a change for you to become a PhD candidate while you enjoyed your free will and leadership, driving your passion and your scientific wish. And you wanted to do the project the way you wanted to find it scientifically profound, at the same time having a good balance between all parties involved, especially your young advisor and also the grant holder. The quarterly reports to the grant holder demanded a lot of challenges and deadlines, and tight deadlines to meet with. They imposed several deadlines were successfully achieved with your time management. And I well remember for one of them, we both did not sleep quite late till morning until we could submit the conference paper right in time. With all the ups and downs, discussions, moments of tight deadlines, you very well managed to successfully finish this journey. And what a journey. And I observed you grow more and more as you jumped over more and higher hurdles. I like the quoted message from Thomas Carlyle in your thesis, no pressure, no diamonds. The work you did is excellent. You not only developed a method, but implemented, benchmarked, tested, and now even you have a provisional patent for your PEDFM fracture model. By the way, you know, all we do belongs to TU Delft. But as such, the patent also belongs to TU Delft. But hey, who cares? You did the invention and published an open access journal paper about it. A work that started from a discussion at Rossio restaurant in Delft behind a napkin, and we figure out that EDFM had leakage and inconsistency. The development of PEDFM and algebraic multiscale method for it also gave you an opportunity to do internship at Chevron, at Houston office. Funny was it, when you arrived there, a hurricane also arrived, so we had to make sure you were safe and well. Congratulations many times for not just doing your excellent work, but being a caring person to your family as well. I remember you had a very close attention to your brother, who ended up studying at TU Delft as well. Also, being TA of Reservoir Simulation course, you were also a very, very helpful member of our DARSim group. In fact, you were the first member of DARSim group. And if you remember, we established it together and we promised to make it grow more and more and more every day. And you know how big we are today. So to me, your work, your stay, your progress were all special. My first very PhD student at TU Delft, with several publications and contributions to the community. Someone coming from Romania, having his master's in math, doing PhD in geosciences, and now living to the company he actually started his whole journey from, Schlumberger. You started with their grant here for 4 months. You did your PhD with ADNOC support and ended up at Schlumberger again. Last thing to say, we agreed on 3 challenges to overcome and have you successfully finish your PhD. Challenge number 1, beat me in table tennis. 2, publish 4 papers. 3, find a girlfriend and bring her to your defense. You did find a very nice girlfriend who is here with us today. You actually not published 4 journal papers, but 5. But unfortunately, you did not beat me in table tennis. Should I accept that? Well, I have a gift for you that I can give you later. I have a table tennis racket for you. And so to remind you that we have still an unfinished business. Good luck with life management after PhD time management. Stay healthy, happy, and wealthy, especially with Schlumberger. And of course, productive. It was my honor to have you here and hope to hear more and more from you for years soon. Congratulations again.
Well, Dr. Tene, you now have the right to use the title of doctor. Your doctorate means that society can rely on your judgment, that you act transparently, and that you independently communicate the results and the social relevance of your work. In other words, your doctorate implies academic integrity. I wish you every success with the responsibilities that come with your new status. On behalf of the Board for Doctorates of Delft University of Technology, I congratulate you and your family on earning your doctorate. Dr. Tene, you may return to your seat in the audience together with the partners. Ladies and gentlemen, thank you very much for your presence. I hereby close this academic session.
Wilt u opstaan?